Okay, going to start working on 8.7. I'm going to look at number 5. So this is the section Taylor-Maclaurin series. So number 5, they give you a function f of x equals 1 minus x to the negative 2. And they want you to find the Maclaurin series and also find the radius of convergence. And we're going to assume that there is a Maclaurin series for this. That's what it says. So, well, what is a Maclaurin series? Maclaurin series is a Taylor series about a equals 0. That's what a Maclaurin is. So what we need to do is we need to rewrite this using the fact that our function should be able to be rewritten as a sum n equals 0 to infinity c sub n x minus a to the n. And here a is 0. So all Maclaurin series look like this. So I need to find the Maclaurin series. So the question is, how do we get these c sub n's? And that's what this section is about. Remember that your c sub n's are equal to the nth derivative of the function at a over n factorial. And here a is 0 because it's a Maclaurin series, so we can replace that a with 0. So what I need to do is I need to take a look at this function. I need to start taking derivatives of it. And as I take derivatives, compute this value, and that should give me what these c sub n's are. And then I can start writing out the Maclaurin series. So let's try and get these c sub n's. So first of all, let's take a look at some of the derivatives. The 0th derivative of the function at x means you don't take the derivative at all. So it's just 1 minus x to the negative 2. Now next to this, I'm going to write down what is the 0th derivative at 0. And you know what, let's just do this. So we've got this equals, plug 0 in here. When you plug 0 in here, you get 1 raised to negative 2. That's just 1. So that's no big deal, just 1. And then we take the first derivative. So now we just bring out the negative 2. 1 minus x. We subtract negative 2, take away 1, we get negative 3. And now what we'll do is we'll figure out what the 0th derivative, or sorry, the first derivative is at 0, because it's a Maclaurin series again. Plug in 0, we get 1 to the negative 3, that's still 1, but then times negative 2, so negative 2. You know what, I forgot chain rule, hold up. Chain rule, derivative of this, negative 2 comes down, derivative of the inside is negative 1. I'm trying to rush through this. So we try and plug in 0, we get the negative and negative become positive, so that's 2. Now I take the second derivative at x, and now watch what happens. This negative 3 comes out and hits, but remember this together is a 2. So when these two hit each other, I have a 2 here really, and that's going to multiply, it's going to be negative 6, but watch the way I write it. I'm going to say 2 times negative 3, and then I have the 1 minus x to the negative 4. So that's this coming out, hitting the 2 that was already there. And then I have the derivative of the inside, which again is negative 1. So on this one, I think I'll clean it up. This is going to be a positive 2 times 3, 1 minus x to the negative 4. And now if I try and take the second derivative at 0, I plug in 0, I get 1 here, and I get 2 times 3 is 6. But I'm just going to put 2 times 3. You'll see why. And then we take the third derivative. Okay, the third derivative at x. So now bring this negative 4 out here, and it'll be 2 times 3 times negative 4, then 1 minus x to the negative 5, but then chain rule, derivative inside is negative 1. So this is just going to be 2 times 3 times 4, 1 minus x to the negative 5. And now if I plug in 0 into that, again, this is going to be 1, and we just get 2 times 3 times 4. And if we continue this, we'll see a pattern here. That if we want to know what's happening at the nth derivative, right, at 0, so I'm trying to figure out a pattern over here. Notice that the 0th derivative we have 1, the first derivative we have 2, the second we have 2 times 3, the third we have 2 times 3 times 4. So the pattern is that whatever this number is, this right here is always that number plus 1 factorial. So this, if we take 2, add 1, we get 3. This is 3 factorial. It's really 3 times 2 times 1. If we take 1, we add 1, we get 2. 2 factorial is 2 times 1. If we take 1 and add it to that, we get 1, and 1 factorial is 1. This one right here, if we add 1 to 3, we get 4. 4 factorial is 4 times 3 times 2 times 1. So this is correct. We see the pattern, hopefully. So what this will be is n plus 1 factorial. So now let's go back and look at what we were supposed to see here. The function should be able to be rewritten as a sum n equals 0 to infinity c sub n times x to the n, where c sub n was the nth derivative at a, which is 0, over n factorial. So I know that these look like this, but we just showed that this is n plus 1 factorial, and then over n factorial, which means that if we peel off on top n plus 1 n factorial over n factorial, they cancel, and so you just get n plus 1. And so my function, this function should be able to be written as sum n equals 0 to infinity of n plus 1 times x to the n. And that would be the Maclaurin series for that function. Now, finding the radius of convergence means that you would run a ratio test on this, which I'm not going to do, all right? But I'll just let you know that when you do the ratio test on this, you get absolute value of x less than 1. So your radius of convergence is 1. All right, so that was the first example. Let's see if we can do another one and start picking up on the pattern here. All right, the next one is e to the negative 2x. F of x equals e to the negative 2x. And so again, we should be able to rewrite this as sum n equals 0 to infinity c sub n x to the n, because it's a Maclaurin series. We have just x to the n, not x minus a. Well, we do, but a is 0. And our c sub n's will be equal to the nth derivative of the function at 0 over n factorial. All right, so let me start getting a handle on these derivatives. The 0th derivative of this function is going to just be the function itself, e to the negative 2x. If I take the 0th derivative and I plug in 0, because this is a Maclaurin series, then I plug in 0 here, e to the 0 is 1. All right, now let's take the first derivative. The first derivative of this function, I have a little bit of chain rule to do here. Derivative of e to the negative 2x is itself, but then times negative 2, the derivative of the top. So negative 2 e to the negative 2x. If I now take that derivative, plug 0 in, This is going to be 1, and I just get negative 2. Now if I take the second derivative, I cover this up, the derivative of e to the negative 2x is again negative 2 e to the negative 2x, but I had a negative 2 out here, so this is going to become a positive 4 e to the negative 2x. And if I plug in to the second derivative 0, I just get 4. So what's going to happen next time? When I do my third derivative, I get another 2 that's going to come out, another negative 2 is going to come out when I do this. If I cover this up, I get another negative 2 coming out. So that's going to turn this into a negative 8 e to the negative 2x. And then if I take that third derivative and I plug in 0, I just get negative 8. And let me just do one more. If I do the fourth derivative at x, am I recording? Yes. That'd suck. Fourth derivative, I get another negative 2 that comes out, so that'll be 16 e to the negative 2x. If I plug into the fourth derivative 0, I get positive 16. So what I'm looking for is a pattern in these, and I think I see it. These are all powers of 2. This is 2 to the fourth. This is 2 to the third. This is 2 squared. This is 2 to the first. This is 2 to the 0. But it's switching signs also. And so it looks like this 0 matches up with this power. This 1 is this power. This 2 is this power. So what I want to do is try and make this thing alternate, starting with positive, then negative, positive, negative, and remembering that my end's going to start at 0. So how can I make that happen? How about if instead of 2, I put negative 1, right? This was negative 1 to the 0, 2 to the 0. That's this one. This one is negative 1, sorry, this one right here is negative 1 to the 1, 2 to the 1. And then this one right here is negative 1, but this time squared, then 2 squared. And then this one right here is negative 1 cubed, 2 cubed. And then this one right here is negative 1 to the fourth, 2 to the fourth. So all of these are just what? Negative 2 to the 0. This one is negative 2 to the 1. This is negative 2 to the 2. Negative 2 to the 3. You may have seen that without me going through all that detail right there. So that's my pattern. So what then can I say about this? What's the nth derivative at 0 going to be? Well, remember that this derivative tells us the power on the 2, on the negative 2. That's all it does. So my c sub n's in this formula, or in this particular function, should be negative 2 to the n. And then it's always divided by n factorial. So we have the original function, this one right here, can be written as the power series starting at n equals 0 to infinity of this negative 2 to the n over n factorial times x to the n. That is the Maclaurin series for e to the negative 2x. And you could find the radius of convergence by doing ratio test. And what you'll find on this one is that the radius of convergence is infinity. So it turns out to be one of those ones where when you run the ratio test and you do the limit as n goes to infinity, that one piece goes to 0, and so x doesn't matter anymore. I got some good markers. Digging through my desk, I found some markers from like several years ago, and they're still good. All right, f of x equals sine of pi x. Okay, this is going to be interesting. All right, so we should be able to rewrite this. Let's just start taking a look at the derivatives. So the 0th derivative of this function is just the function itself. And if I plug 0 into this, sine of 0 is 0. All right. Now the first derivative. First derivative of this, well, derivative of sine of something is cosine of it, but then the derivative of the inside here would be pi. So I'm going to get pi cosine of pi x. And now when I do the first derivative at 0, cosine of 0 is 1, but then times pi, so I have pi. Now when I take the second derivative, what's going to happen is I'm going to get, pi is going to be here, derivative of cosine of something is negative sine, but then derivative inside is a pi. So I'm going to get negative pi, that's the derivative of cosine is negative sine, the pi that was here, it's going to be sine of pi x, but then times the derivative of what was in here, which is another pi that I can put out here, or I can just square that. And now when I take the second derivative and I plug 0 in, it's not going to matter because sine of 0 is 0, so this is 0. Now we do the third derivative. And what we do is we keep doing this until we find enough of a pattern. So when I take derivative of sine of something, it's going to be cosine of it. And then the derivative inside, I'm going to have a pi. That pi is going to come out and join this one. So I'm going to have a negative pi cubed cosine of pi x. And when I take this third derivative and I plug 0 in, this time cosine of 0 is 1, I get negative pi cubed. All right, so next one. Fourth derivative. Okay, this time take derivative cosine and get negative sine. The negative is going to come out right here and make that a positive. So positive pi sine of pi x. Derivative of the inside is another pi, and I had pi cubed out there, so pi to the fourth. And it won't matter because when I take the fourth derivative and I plug 0 in, it's going to kill everything off. I get 0. One more. Fifth derivative. Okay, so fifth derivative of sine is cosine. The pi is going to pop out, so pi to the fifth, cosine of pi x. And then when I plug in 0 into this, I just get positive pi to the fifth. Now it's a little harder to get a pattern on this one directly, because what you see is that when we plug in 0, we get 0. When we plug in 1, we get pi. 2, we get 0. 3, negative pi cubed. 4, we get 0. So at every even number, we're getting 0. At every odd number, we're getting something to do with pi. And it looks like it's alternating also. So notice here, right, I'm circling all the odds. Okay. Hold on, let me take this call real quick. This one's a little bit harder to pick up, like I said, because what's happening is we do have a pattern, but it's only occurring at odd derivatives. So the best way that the way that I like to approach this is I like to write out what this series is supposed to look like. Okay, so we know that this is supposed to be the sum n equals 0 to infinity, right, of c sub n and then x to the n. And I can tell, well, you know what, this should be c sub 0 x to the 0 plus c sub 1 x to the 1 plus c sub 2 x to the 2 plus c sub 3 x to the third plus dot dot dot. Now, remembering the fact that c sub n is the nth derivative at 0 over n factorial, that means c sub 0 would be the 0th derivative at 0, which is this, which is 0 over 0 factorial, which is 0 over 1, which is just 0. So my first term here is going to be 0 times x to the 0. That's just 0. Plus, now c sub 1 is going to be the first derivative at 0, which is pi, over 1 factorial, which is just pi. And it's positive, right? So pi. And then that's pi, and then x to the first power. Then when I do c sub 2, right, it's going to be the second derivative. That's going to be 0, so I'm not going to have anything. Plus, now when I do c sub 3, watch what happens. C sub 3 is the third derivative at 0, which is negative pi cubed over 3 factorial. So this should actually be, I'm going to change this plus to a minus, minus pi cubed over 3 factorial x to the third power. So that's this one. And now I need to keep going to try and really get this thing under control. The fourth one is going to be 0 because we knew that from all the evens being 0. The fifth one is going to be c sub 5 is going to be the fifth derivative at 0, which is this, pi to the fifth over 5 factorial. So that's going to be pi to the fifth over 5 factorial, and then x to the fifth. And what do we think the next one's going to be? For 6, it should be 0. And then we're at the 7th one, right? So we should have, it's going to alternate. We're going 0 and then positive, 0, negative, 0, positive, 0, negative. So I should have negative pi to the 7th over 7 factorial x to the 7th plus dot, dot, dot. And that keeps going. So let me now rewrite this. Get rid of all those zeros. Pi x minus pi cubed over 3 factorial x cubed plus pi to the 5th over 5 factorial x to the 5th minus pi to the 7th over 7 factorial x to the 7th plus dot, 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 dot. And what I'm going to do now is I'm going to just use my ability to rewrite the sum using sigma notation. And I'll start it out at n is 0 to infinity. And I want to create an alternating series. And I want to start with positive. So to do that, I'm going to go negative 1 to the n. I want to start at positive 1, or positive. So negative 1 to the n, if I start with 0, I get a positive 1, and then if I go with n is 1, it will be negative, then positive, then negative. So this should create the alternating part. Then I have here, all these powers on the pi's are all odd numbers. So I need to do pi raised to odd numbers starting at 1. So 2n minus 1. If I plug in, plus 1. If I plug in n is 0, I get 1. n is 1, I get 3, n is 2, I get 5. I want to divide that by all of these are odd factorials, including underneath this pi there's a 1 factorial. So these are all odd factorials starting at 1. So again, 2n plus 1, but then factorial. And then all of the powers on the x's are odd. So I have x to the 2n plus 1 again. And that should do it. That should be my power series right there. What number was this? Good. And maybe I have time for one more. Yeah, let's try and do one more. This one's going to be nasty. Number 8. So that problem was an example of one where you have to write out the terms in order to pick up the pattern and to be able to rewrite it easily. So I'm looking at the function x cosine x. And I'm trying to write the Maclaurin series out for this. And so I need to start getting derivatives again. So the 0th derivative of this function is itself. And then the 0th derivative at 0, thank goodness, because it's a Maclaurin series, is going to be 0. Now the first derivative, I'm going to move over here a little bit, the first derivative of this function requires a product rule. So the derivative of the first one is 1 times the second, plus derivative of the second one, which is negative sine x, times the first one, so negative x sine x. Now, if I take that first derivative and I plug in 0, this goes away, but cosine of 0 is 1, so I get 1. Now the second derivative. These derivatives are going to start to get ugly. Okay, derivative of cosine of x is negative sine x. And then I have minus, in parentheses, a product rule right here. So the minus I'm not looking at. Derivative of x is 1 times sine x, plus derivative of sine x, which is cosine x, times x, so x cosine x. And cleaning this up, I get negative sine x minus sine x again, minus x cosine x, which is going to turn into negative 2 sine x minus x cosine x. That's the second derivative. And now if I plug in to the second derivative 0, this is 0, and that's 0. So I get 0. Great. All right. Wait a minute. Yeah, that's the second derivative. All right, so now the third derivative. The third derivative is, okay, derivative of negative 2 sine x is negative 2 cosine x minus the derivative of x cosine x. Wait a minute, that's the original function. What was the derivative of the original function? It was this. So I have minus, and so I don't have to do the work again. I just look at that first derivative, which is this. So minus cosine x minus x sine x. And cleaning up here, let me see what I get. Distribute the negative through, I get negative 3 cosine x. And then here to here, plus x sine x. If I plug in to this, 0 kills this off. Cosine 0 is 1, I get negative 3. All right, so let me write down over here so I have it. I have the 0th derivative at 0 is 0. The first derivative at 0 is 1. The second derivative at 0 is 0. The third derivative at 0 is -3. I'm hoping that when I do the fourth derivative, I get 0 again. Fifth derivative, maybe I'll get +5, right? 1, -3, +5, -7 when we do the seventh derivative. I need enough to pick up a pattern. So let me keep going here. I'm at the fourth derivative. Crap, I just erased some stuff I might need. The fourth derivative is the derivative of this. Well, the derivative of -3 cosine x is going to be +3 sine x, and then plus the derivative of x sine x, which I've done before. I'll do it right now. It's going to be sine x plus x cosine x. So I had to do product rule on this. And then when I put those together, I get 4 sine x and then plus x cosine x. Now if I take that fourth derivative and I plug 0 in, this is 0, that's 0, so I get 0. So it's exactly like I thought it was going to be. Fourth derivative at 0, 0. And I'll do the derivative maybe one more time. If I get a +5, I'm going to feel good about what's happening here. So the fifth derivative at x, the derivative of sine of x, cosine of x, but there's a 4, so 4 cosine x. And then plus, now product rule on this, we've done this already, it's cosine x minus x sine x. And then when we put these two together, I get 5 cosine x, then minus x sine x. And now if I take that fifth derivative, I plug 0 in, this goes away, I get cosine of 0 is 1 times 5, I get 5. I think, are you happy that what we're having is all the evens are 0, all the odds are just, 1, 1, 3, but this time -3, 5, 5, next one should be, 6, 0, and then 7, -7, then 8, 0, then 9, +9. So let me start writing out this Maclaurin series. So I know that I'm going to have this f of x, x cosine x, should be equal to, remember I'm getting my c sub n right now, so it's the 0th derivative at 0, which is 0, over 0 factorial x to the 0, plus now the first derivative at 0, which is 1, over 1 factorial x to the first, plus now 0 over 2 factorial x squared, then plus, let's see, actually we know what's going to happen with the third, I'm going to get minus. So minus 3 over 3 factorial x to the third, and then plus 0 over 4 factorial x to the fourth, and then the 5 was a positive, so plus 5 over 5 factorial x to the fifth. I'll do 2 more. Plus it should be 0 over 6 factorial x to the sixth, and then the next one should be minus 7 over 7 factorial x to the seventh, plus dot dot dot. Now let me rewrite this with all the zeros gone. So this is gone, this is gone, this is gone, this is gone. So we have 1 over 1 factorial x to the first minus 3 over 3 factorial x to the third plus 5 over 5 factorial x to the fifth minus 7 over 7 factorial x to the seventh. What would the next one be? 9 over 9 factorial x to the ninth. Next one, minus 11 over 11 factorial x to the 11th plus. And now I need to come up with a formula for this. I'm going to start my index at 0 and go to infinity. So, well, this is odds again, right? I've got odd number. Let's look at this one. Odd, 1, 3, 5, 7, 9, 11. Oh, the alternating. Oops, I should take care of the alternating. I need to start with a positive, so negative 1 to the n will work. And then all the odds, starting with 1, so 2n plus 1 over all the odds again, factorial. And then all the odds again on the power of x, starting at 1. Okay, that's fine. That's good. Looks very similar to the last problem. Which one is this one? 8. Yeah, it's similar to the last problem. Now there's something we can do here, which is kind of nice. I don't know if you noticed this, but like all these factorials, like this is 3 times 2 times 1. This is 5 times 4 times 3 times 2 times 1. Like this 3 and that 3 would cancel, that 5 and that 5, and then this 7 and the first 7. So what you'd be left with here is 2 times 1. This one would be 4 times 3 times 2 times 1. This one would be, what, 6, because the 7s would cancel. 6 times 5 times 4 times 3 times 2 times 1. You can see it another way if you just look at your formula here. Negative 1 to the n times 2n plus 1 over, let's rewrite the bottom as 2n plus 1. Peel off 1. 2n factorial x to the 2n plus 1. So I'm just breaking this factorial down and noticing those two would cancel. So we get sum n equals 0 to infinity, negative 1 to the n, and then that cancels, so I have 1 over 2n factorial x to the 2n plus 1. Ratio test on this, if you did it, radius would be, that's an infinity. I think I can do 9 pretty quickly. Try and get 9 done. Sine hyperbolic, or hyperbolic sine. This one's going to be a lot easier than the one we just did because of the derivatives. The 0th derivative of this function is cosine hyperbolic x. If you plug in 0 into the hyperbolic, you have to remember what the hyperbolic meant. So, do you remember what cosine? Oh, why did I do that? Oops. I said it would be easy. Okay, the 0th derivative is actually nothing happens to it. And if you plug 0 into sine hyperbolic, you get 0. So go back and look at the definition of sine hyperbolic. We did that earlier this semester. It involved powers of e. So if you plug that 0 into it, you'll get 0. And then when you take the first derivative, the derivative of that is just cosine hyperbolic x. And if you plug 0 into that, you get 1. And the thing about sine hyperbolic and cosine hyperbolic is that the derivatives just keep on flipping back and forth from one another. They don't ever change signs. So the next derivative will be sine hyperbolic x, the next derivative cosine hyperbolic x, the next derivative sine hyperbolic x. And so what happens over here is you just get 0, 1, 0, 1, and you keep on going. Golly, Robert, 1. I'm hungry, it's late, I need to get home. And so what I'll do is just write out this Maclaurin series, and then I'll try and come up with a formula for it. So I know that this is equal to, all right, c sub 0, which was the 0th derivative at 0 over 0 factorial, which is going to be, we said that the 0th derivative was 0. So this is just going to be 0. So I'll write it down over here. 0 over 0 factorial x to the 0 plus, now this time we're going to get a 1 over 1 factorial x to the first plus this time a 0 over 2 factorial x squared. And it just, we keep on getting 1s and 0s. So 1 over 3 factorial x to the third plus 0 over 4 factorial x to the fourth, and then plus 1 over 5 factorial x to the fifth plus dot dot dot. Get rid of all the 0 terms. So you get 1 over 1 factorial x to the first plus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth plus 1 over 7 factorial x to the seventh, and you keep going. And now I'll come up with a sigma notation for this. Man, this odds is a big thing. Now notice all of these are always 1s. So I'm just going to have 1 over, now these are odd factorials starting with 1. So 2n plus 1 factorial, and then the powers on the x's are all odds starting with 1. So that should be it. That's your Maclaurin series for the hyperbolic sine function. Now, I think I'll skip 10, because 10 is just like this. It's cosine hyperbolic. So the only difference between this one and cosine hyperbolic is that you're going to have 1s here and 0s here. 1s and 0, 1, 0. So it's going to change, but I'll leave that to you to try and figure out. There's no magic in that. And that's it for this video. I'll pick up on number 11. I'm going to try and do 11 through 18. And then I'm also going to try and do 27 through, I don't know, 35 or so. All right, that's it.